Take a molecule of ethane. At room temperature, it's a simple, largely unreactive gas. But swap out a single atom, and suddenly you have a heavy liquid that fuels a combustion engine or acts as a powerful industrial solvent. That massive shift in physical behavior comes down to one tiny adjustment: trading a hydrogen atom for a hydroxyl group, an oxygen paired with a hydrogen, usually written as OH. This pairing defines an alcohol, an organic compound where the hydroxyl group attaches to an sp3 hybridized carbon atom. This carbon is anchored by single bonds to 4 other atoms, giving it a specific 3D shape. Understanding alcohols means tracing how this single molecular attachment controls everything from how a chemical physically moves to its immense utility in our daily lives. If we look at this reference chart, the top right panel shows the IUPAC naming rules for these molecules. We select the longest carbon chain containing the hydroxyl group, drop the standard E ending, and add the suffix OL, turning methane into methanol, or ethane into ethanol. Chemists classify these structures first by quantity. Looking to the left panel, if a molecule has 1 hydroxyl group, it's monohydric, 2 makes it dihydric, and 3 makes it trihydric. But the second classification method is much more critical. Here in panel 2, we categorize them by placement. Depending on whether the carbon bearing the OH group is attached to 1, 2, or 3 other carbons, we classify the alcohol as primary, secondary, or tertiary. This architectural placement dictates the molecule's chemical destiny. Whether an alcohol is primary, secondary, or tertiary strictly determines its reactive potential. To fully grasp how these specific 3D architectures operate, we have to look at how chemists synthesize them from other molecular precursors. Back on our chart, panel 4 shows one common preparation method: the acid-catalyzed hydration of alkenes. By adding water to a double-bonded alkene like ethene in the presence of an acid catalyst, we break the double bond and attach our hydroxyl group, producing ethanol. Moving to panel 5, an alternative method is reducing carbonyl compounds. Here, reducing an aldehyde reliably yields a primary alcohol, while reducing a ketone yields a secondary alcohol. Panel 6 highlights an even more precise method. By using organomagnesium compounds known as Grignard reagents, chemists can custom build primary, secondary, and tertiary alcohols depending entirely on which starting material they choose to react it with. By mastering these distinct input reactions, chemists can engineer the exact 3D alcohol architecture required for a specific application. Once synthesized, that hydroxyl group starts exerting immense control over how the molecule behaves physically in the real world. It starts with the highly polar nature of the OH bond itself. The oxygen atom is highly electronegative. It hogs the shared electrons in the bond. This creates a localized charge imbalance, giving the oxygen a slight negative charge and the hydrogen a slight positive charge. Because of this imbalance, the positive hydrogen of one alcohol molecule is attracted to the negative oxygen of another. This creates intermolecular hydrogen bonding. The molecules act like tiny magnets, aggressively sticking to one another in a dynamic network. This chart panel shows how that microscopic sticking translates to macro-scale physical properties. Because the molecules hold onto each other so tightly, it takes significantly more heat energy to pull them apart, resulting in higher boiling points relative to their mass. It also allows lower mass alcohols, containing 1 to 3 carbons, to seamlessly dissolve in water, since they form those same hydrogen bonds with the water molecules. This subatomic polarity explains the contrast we saw at the beginning. It is the reason ethanol is a heavy liquid capable of forming solutions, while nonpolar ethane remains a volatile gas. That same polarity makes the hydroxyl group a perfect reactive handle for chemists to grab and manipulate. Taking a look at panel 9, we see foundational substitution reactions. We can react an alcohol with sodium, substitute the hydroxyl group using hydrogen halides, or use thionyl chloride to form entirely new alkyl chlorides. Moving to panel 10, we can even rip the water out entirely. By reacting an alcohol with concentrated sulfuric acid at 443 Kelvin, we undergo dehydration, eliminating the OH group and reverting the molecule back into a double-bonded alkene. Alcohols function as versatile chemical transit hubs. In organic chemistry, they provide the starting pathways used to manufacture entirely different families of compounds. But remember that structural architecture we classified earlier? Whether an alcohol is primary, secondary, or tertiary strictly limits what it can become during its most common transformation, oxidation. The lower half of panel 10 maps these strict boundaries. Primary alcohols oxidize into aldehydes and can oxidize further into carboxylic acids. Secondary alcohols will only oxidize into ketones, and tertiary alcohols simply resist oxidation under ordinary conditions because their central carbon has no hydrogen left to lose. Chemists prove these invisible structural differences in real time using the Lucas test, shown here in panel 11. By mixing the alcohol with concentrated hydrochloric acid and zinc chloride, they watch how fast turbidity, or cloudiness, appears. Tertiary alcohols turn cloudy immediately, secondary take 5 to 10 minutes, and primary alcohols show no turbidity at room temperature at all. This precise control over their reactivity allows us to utilize alcohols across almost every industry, synthesizing them into bulk solvents, into automotive antifreeze, into medical antiseptics and high combustion fuels. Every industrial solvent, every synthetic pathway, and every unique physical property we've explored stems entirely from one source: the precise geometry and polarity of that single powerful hydroxyl group. Hydrocarbons like ethane and propane are mostly happy just existing. Without modification, these compounds are usually inert gases or liquids, offering very little chemical versatility. But if we introduce an oxygen and a hydrogen atom, a hydroxyl group, and attach it to an sp3 hybridized carbon atom, the molecule's entire personality changes. This single attachment transforms a dormant hydrocarbon into a highly reactive compound known as an alcohol. Looking at these structural formulas, the exact placement of this OH group dictates the molecule's specific identity. A primary alcohol has the OH attached to a carbon bonded to one other group, a secondary connects to 2, and a tertiary is crowded by 3. To keep all these variations straight, chemists use the IUPAC naming system. By adding an all suffix and a position number, we get a universal language. A formula turns into a specific, readable name, like ethanol or propantuol. The placement of one tiny atomic group dictates a molecule's entire physical destiny and chemical potential. Zooming in on the atomic mechanics of the OH bond, we find a microscopic tug-of-war. Oxygen is highly electronegative, meaning it pulls electrons away from the hydrogen. This creates a polar bond, leaving the oxygen with a partial negative charge and the hydrogen with a partial positive charge. Referencing this diagram, this polarity allows molecules to act like magnets. The negative oxygen attracts a positive hydrogen, forming strong hydrogen bonds. Breaking these connections takes real energy, giving alcohols significantly higher boiling points, which climb even higher as molecules get heavier. This polarity also explains how they interact with water. Lower mass alcohols, those with 1 to 3 carbons, can easily form hydrogen bonds with H2O molecules, making them completely soluble in water. But as the carbon chain grows longer and heavier, that solubility drops. The increased mass causes the physical state to shift, turning higher members of the alcohol family into heavy liquids or waxy solids. Physical properties like boiling point and solubility are direct mathematical consequences of a polar structure. If the OH group dictates all these properties, we need to know how chemists actually construct these molecules from scratch in a lab. One common method is acid-catalyzed hydration. By applying water and an acid catalyst to a simple double-bonded alkene, chemists can force an OH group and a hydrogen atom onto the carbon structure. Another method involves preparing them from carbonyl compounds. Reducing an aldehyde yields a primary alcohol, while starting with a ketone will produce a secondary alcohol. For building complex, customized structures, chemists turn to Grignard reagents. Looking at these 3 reaction pathways, you can see how modifying the starting material with a Grignard reagent determines exactly whether the final product will be a primary, secondary, or tertiary alcohol. Chemical preparation operates like a microscopic construction site. Chemists select very specific precursor molecules to engineer the exact functional tool they need. Once built, that polar OH bond makes alcohols highly reactive. They are weakly acidic, meaning they will readily react with active metals like sodium to form compounds called alkoxides, releasing hydrogen gas in the process. They can also be deconstructed. Treating an alcohol with concentrated sulfuric acid aggressively rips away the OH group and a neighboring hydrogen. This dehydration process reverts the molecule back into a double-bonded alkene. Then there is oxidation, an upgrade path limited by the alcohol's structural classification. Primary alcohols easily oxidize into aldehydes, then carboxylic acids. Secondary alcohols stop at ketones. Tertiary alcohols, lacking a free hydrogen, resist oxidation almost entirely. This difference in reactivity is the basis for the Lucas test, a practical diagnostic tool used to blindly identify an unknown alcohol. Because tertiary alcohols react instantly to form a cloudy solution, while secondary alcohols take minutes and primary alcohols require heat, chemists can identify the microscopic anatomy just by watching a stopwatch. Molecular anatomy dictates exactly what a compound can do and allows us to definitively identify its hidden structure through macroscopic observation. Stepping away from the equations, these structural mechanics are the invisible engine powering massive sectors of the modern economy. Methanol, the simplest alcohol, is a heavy lifter in industry. It is used as a widespread solvent, a commercial antifreeze agent, and a necessary precursor for manufacturing formaldehyde. Ethanol steps into consumer and medical roles. It serves as a critical biofuel source, a reliable medical antiseptic, and is the foundation of the global beverage industry. The immense complexity of our material world is driven by the exact placement of a simple OH group. Mastering alcohol chemistry means mastering one of the most practical building blocks of reality.